is your name, right?
Yes. Hello, my name is Joaquin, and I'm the host of the AI Digest. With me today is Hala Nelson. Hala is a mathematics professor at James Madison University, and she is also the author of a book called Essential Math for AI. Hala, it's a wonderful pleasure to meet you for the first time virtually, but I'm very excited because as we've spoken, I just get this genuine sense of enthusiasm. So it's a pleasure to have you.
Thank you, Joaquin. It's so nice meeting you as well, and I'm excited to chat with you.
Um, so Hala, uh, we communicated over email initially to get a better idea of what we want to cover, and I think that there's a really good blend of mathematics, artificial intelligence, and then the more concrete aspects of how to use these ideas in the real world. So let's start with the book that you released, Essential Math for AI. And I want to understand, what is essential math? Do I have to
Uh-huh.
do derivatives? Do I have to do calculus? What do I have to do?
That's yeah. People always ask me that, and I one of the reasons I wrote the book is to tell people that you don't have to go and have a PhD in math to be able to understand and explain AI or even use AI. But I wanted them to also not use it. Without any background knowledge, and I wanted them to be informed enough and knowing so as not to just like grab things and put things together that would never work together or that would lead to bad outcomes. So yeah, the math, so people tell me, what is essential math for AI? And I'm like, you have to understand how the what is AI and what you want out of your AI system. And then in terms of math, you have basically two paradigms, deterministic, probabilistic. And if you understand them and how they are different from each other, and what what goes into each, then you would be okay. You would, if you only understand these two concepts, and then you understand also the concepts of linear models and nonlinear models. The linear is flat and nonlinear is more like complex, and depends what kind of uh, data you're dealing with, what kind of tasks, what kind of inputs, outputs, etc. uh, if if you know these like very small categories, not much, then you would understand the foundation that the whole AI world is built on. Um, and to be more concrete, you would need, so when I say a probabilistic model, you would need to understand what the joint probability distribution is. For example, what is the likelihood that I will get this outcome based on this data features, based on observing this data features? You're observing them. And if you're deterministic, you're asking question is exactly how do these features interact together? Give me the formula of their interaction. And that's a deterministic function. So the input are the data features and the output is a deterministic function that will always give you the same answer every time you put these features in. You get that outcome, whether you're classifying, whether you're predicting, whether you're driving an autonomous vehicle, move left, move right. It's really always the same. So if you understand the concept of a function you were talking about before we started the recording, of the input output, that really is like, if you think about all kinds of in math, like you have you talk about functions all the time, and the function is just like you get the input, something happens to that input, and then you produce an output. And in the whole data landscape in AI, you're always dealing with a system. Even the data engineering landscape, you have like some raw data, and then stuff happens to it in the databases or in the whatever, and then you have this nice data comes out on the other end ready for your models and stuff. So it all like once you understand these like fundamental ideas, and I do spell them out clearly in the book, then you have a basis for both math and AI, which is amazing. It's like you benefit in both. You would understand AI 100 times better, but you will also have an amazing intuition for math as a whole and how it all relates to each other. In my opinion, AI demystifies math, and math is the foundation that AI is built on.
That's that's a lovely introduction to the book, and I think you covered some pretty essential concepts that can be chained together to reason, through natural intelligence, through just, I want an exact outcome. How
Yeah,
do I determine that? Deterministic. How do I determine that with the variables that are on the table?
exactly.
Or probabilistic, statistically,
Yeah,
if I can imagine that this is the likelihood of this kind of event to happen, how do I
yes,
reason with this as possible outcomes that I need to manage as risks to a project, or I'm going to win the lottery, or
yeah,
this kind of event will occur? That's really, even outside of AI, even outside of just those things, we live in a world of systems. So I think you're bringing a lot of perspective to people to understand that, for us to work with systems, through systems, there needs to be these fundamental concepts, sort of laid out for them. Uh,
definitely. And let me just add that people think that it's either or. There is a community that only does probabilistic models, and there's a community that only does deterministic models. They don't know about each other. They
mhm.
don't. They cannot like get the benefits of each other. For example, the people doing generative AI, they're always like learning a joint probability distribution, say, of language, and then sampling words from that probability distribution that they learn. So that's a generative is most of the time probabilistic, but of course, when you're sampling from probability distribution, you're always gonna sometimes samples that are bad samples, so you don't want them, and that's how hallucination happens. But then you can build on top of that, and what they're doing now is building on top of that some knowledge graphs to fix that. They're building a deterministic object on top of that, random thing. So when you kind of do the both strengths together, it always you can leverage both to get better outcomes, to get what you want. And if you have, what I tried to do in my book is to not to tell people it's either this or that, it's one community. Wanted people to know the whole landscape, and then how they relate to each other and how they can use from each. And some people ask like, well, how do you know which one to use? Like if you have a deterministic model and probabilistic model that can do the same thing, for example, that can do the same task, like how do I know what I should put in my system? So they for the simplest example I can give on that, like clustering, like k-means clustering is a deterministic algorithm, and Gaussian mixtures is a probabilistic algorithm, and they both with the same data set they would give you clusters, but the clusters here will be different than the clusters here. And how do I know which one to use? Should I go with the probabilistic clusters and classify things there, or should I do with the deterministic? And it's the exact same data set. So you're like, well, you have if you have time, test both. If you have, it depends. If you have computational resources, and then go and see which one is performing better. And there are people like who tested both on their cloud center workloads, and they discovered that the probabilistic model for that particular use case is doing better on the edge cases, right? Usually the far things apart are clearly separated, but usually the edge cases is where the questions are. So, but in my book, I try to give people a good understanding of all of this, that they can go and check they can experiment. So that's also one of my messages to people, and how I see people apply this in the real world. um, it doesn't have to be wars or either or oh, this is vogue now. No, these are all methods, and these are all really good ideas that you it's a put it in your toolbox and see when you need something to pull it out. Just train your brain to think that way.
I appreciate that you're saying that it's not so cut and dry to say which is better
Yeah,
forever dogmatically.
yeah,
It is, will this work? Number one, will this work for the particular use case?
yes,
Will it meet the desired outcomes?
yes,
And then does it fulfill the constraints of my capabilities, my organization, my strategy, my timelines, computational power, all these
100%.
different constraints, right? But if
Yes.
you have the budget, do them both, see which one works better,
Yeah,
and then
explore it. But if you don't, then you have to sit and think, and having the understanding of what each model does, it will give you a good insight on which one to use when.
just because you start with one doesn't mean that you can't
Oh yeah,
eventually try the other one. It's not
yeah,
a,
yeah.
oh my god, life or death. It's what do I do today and what do I do tomorrow?
I couldn't agree more. And I've done that even with like real big projects, consequential projects for I mean, with the real data, all of that. So it really is. I couldn't stress that enough. And I notice that people come from academia, from school, for example, graduate, and then they go and start applying only the methods they've learned, and they don't know that the whole world out there of models. So, but that world is overwhelming, and they're like, well, which I don't know. I mean, it's a big sea of knowledge, but if you boil it down to the fundamentals, you learn that if and I did that in my book. You just you learn that it isn't much. The fundamentals are very strong fundamentals, and there's only like 4 or 5 essential ideas and things you need to differentiate with, and then all the models, hundreds of models, they spring out of there. And then the differences between the models, like, oh, what am I assuming on this function, how am I splitting the distribution, right? So it's simple differences, simple assumptions that differ from one to the next. And it doesn't mean that the whole community is now going to have to specialize in, say, rags for AI, right? No, it's just, what is the idea? All right. And the ideas are very simple. Most of AI models are moving, the input is data features, the output is a vector that gets saved in a vector database, but the vectors are boiling these hundreds or thousands or millions or billions of features into their essential vector of numbers that each number is capturing, or the dimension, each dimension is capturing or summarizing the essential information in the big data feature. So basically, and when you notice that even a convolutional neural network is moving from pixels to a vector of numbers, or singular value decomposition, which is principal component analysis, which was, you can consider it old and traditional, it still is moving a bunch of data features into a vector of numbers in the principal component direction. So when you see that, even like whether you're like all the way super modern AI or what's considered old, they're still doing the same thing, but one of them, the input is a data feature, the output is a vector of numbers that capturing essential information. Is how you're moving from here to here, you're changing the function in the middle, right? And how you're doing mathematically, I mean, you can change the function anytime you want. And then as long as you know exactly what the function, what the assumption in the new function is it linear, is it nonlinear? How, I mean, so in math, oh, I sure, let's change this. It's easy, right? So suddenly you're not doing the hard stuff or like rocket science. I mean, rocket science is like that eventually. All mathematical, models. So
I appreciate that you're boiling it down to there is a working model of working within the real world, and
Mhm.
it only has four or five
Yeah,
core essential
yeah,
elements that you have to move in terms of levers. Anything stemming from that is just a, a multiplication of all the possible combinations of those
exactly.
essential things.
Tuning,
Um,
exactly.
so let's talk about the Substack that you are writing in. I mean, I think you've showcased your deep and thorough and expansive knowledge on computational theory and all these different technologies. But what you were saying earlier, tell us a little bit about foundations of AI, data, and information.
Yeah, definitely. So this I actually love even more than the first work, because it's nice to build a foundation for everything, for the math. The what math goes into AI is all great. It's all you can understand. You can look in the black box. There is no more black box. So after you read the first book that I wrote, there is no more black box. I don't even use that word. I know exactly what's in the model. I know what it's doing. I know what how this feature is contributing to that output. Right. So explainable AI, let me sit down and explain it, because don't say there is no explainable AI. I can convince you mathematically that there is AI is explainable, and I will be writing about that soon. Now, what happened is I realized that my background is in math, in mathematical modeling, in material science. I realized that I don't know the data. I don't know the data world, and in order to really be successful in AI, if you want to implement AI into your organization successfully, you have to have the right data infrastructure for the AI models to be like. If you want to automate everything, if you want to like take the most advantage of all of that, so I realized that I don't know the data infrastructure. Um, I don't know. All I knew back then is that give me the data set. Like I ask for data and say from the organization I'm working with, say with the fire department or with the military, or give me the data and I get the nice data that I want and I make it better. You don't get it like exactly as you want. You have to do a lot of cleaning. You have to do joining. You have to build your model yourself. However, what happened between the sources of this data and for me to get a file that has data in it, right? Whether it's CSV or whether it's a bunch of images or whatever it is that I get, there's a whole road in between that I don't know. And if something goes wrong in that road, then what I get will be horrible. And I did get a very bad thing like that. Like we worked with the transportation department. I've talked about that in other podcasts. Um, we got data from the transportation department and we did the models and everything, and right before we were about to do the results and present them to the head of the transportation department in the city, we realized that the data that we were given, like the actual bus stops, were not on the bus routes, like the actual CSV file that we received. And of course, that is a scrambling that's happening at the database level. And I had no idea what database they use, how do they record data, like. So I realized that, wow, and when you're only at the level of asking for data, getting it, and applying AI models or non-AI models like analytics, say whatever you want to apply to it, as long as you're at that level, you're heavily dependent on what's happening before you and for it to happen correctly, and you cannot automate the process, right? You cannot, like, how are you gonna, like, AI is all about automation, and the potential of AI is to like have this automation, and you cannot really automate anything if everything is happening separately. And I know for a fact that the people on the data infrastructure, they don't know what we're doing, because and we don't know what they're doing, and the people here, we are sitting in the middle with the enterprise level, like the organizational, like goals, mission, budgets, priorities, strategy. So I realized that, hey, wait a minute, no one has ever, everybody's specializing in one portion of this whole thing that needs to be talking to each other and functioning coherently and properly for for us to take most advantage of these technologies and to actually advance them. um, so I realized that since no one has done that, so I actually sat down and I started learning. Um, Imagine being like a mathematician learning about engineering and things that I never really like. I make my husband do things. I don't want to like do things myself with my hands. I just tell them like, oh, this is how I think it should be done, but I've never really like did it. So it was a jump in a way, I think, and it was a jump that I always felt like it was a gap I had, and I filled it up. I learned like data engineering. I'm not an expert, but at least I know what I need to know for me to like make AI useful. And also I also learned at the top what happens. Like I'm involved in building data strategy, building AI strategy, and aligning it with mission value and with like the values and the goals of the actual institution. So when you have that vision, it's a lot of knowledge and it's actually really nice. And I wanted to write this Substack and the new book to teach people. And also, there's also the idea of communication and information I mean, think about how we communicate now and all the infrastructure that we built for our communication systems, and how I'm seeing you now, and that wasn't possible 20 years ago where I came from, you know what I mean? So all of this infrastructure that we built, I think we can do a we can enhance it a bit better for AI systems to be just built into everything and for them to work. So I do feel like we need to work more on the communication infrastructure, information. There's also like looking all the way into the future. There's also like the potential of quantum computing and all of that, and that does relate. Like if you understand how like bits and bytes are working at the fundamental level, how they're moving around, all of that, and what would how would quantum computing be different, and how would information be stored in a quantum computer, and how would it be processed. So I feel like building again, and I do it in the same way I did in the first time. I do it. I boil it down to the fundamentals. I'm not gonna write encyclopedias, but I do think that all of this, the fundamentals of all of this, has to be explained in one place, and the whole pipeline from all the way from raw materials and down the minuscule level all the way to the organization and its goals and its strategies, even governments, even humanity. So for me, it's that that next goal, and I like this. I'm excited about writing this.
What I really like about math as an idea is that it's pure.
Mhm.
It is free from restraint,
Yes,
and you can think about things how you reason, and you can expand or contract your reasoning according to evidence that you collect through the real world. Applied mathematics is physics, and physics is the mechanics of the universe, what's measurable, how things function in relation to other things.
yes,
Um, I really appreciate you saying it was the fragmentation of working within organizations and sort of working at just one part of the value chain of
yes,
taking data and making it useful or making it um, actionable decision, to help decision making, because that's what do we need data, what do we need information for?
oh
To
yeah,
make decisions, actions.
yeah.
So it's really interesting that that's what led you to want to educate and consolidate all these fragmented things. I mean, it's silly if you think about physical infrastructure. Those problems occur, but they occur far less because you if you're a plumber, you have to reason with the schematics of an architect. How
Yeah,
would you like this water system installed? Where's the clean water coming in and where's the dirty water coming out?
exactly.
But when it comes to virtual or digital disciplines, which is the equivalent of data plumbing,
Yes,
people can visualize where does the clean data come from? Is the clean data coming from a sanitized place? Is it coming from a place that can be interpreted or that I can access to see how it's set up? And how
exactly.
does the dirty data get dealt with so that it doesn't contaminate
Yeah,
the cleanliness of what we're trying to do?
yeah.
Um, so I just wanted to add to that because you triggered some memories and ideas. But tell me about your profession as a professor. Tell me about what kind of classes you teach and where do you focus your efforts in the academic world?
Yeah, as a professor, I am. So yeah, I'm a math professor. I teach a lot of math classes, but I also try. Like for me, some of the most important classes I teach is when students work on real life projects with real uh, entities like government entities or military or like departments, infrastructure departments. So in these projects, students do learn about the value chain. They do learn about, they themselves talk to the decision makers. I teach them. Basically, your project is not going to go anywhere if it's not completely aligned and speaking the language of the institution that you're consulting for or working for. Um, and also there is an advantage that they learn is when you're working doing projects for an institution like that or an entity, um, you have an advantage over their own employees because you're not, the people you're talking to are not your bosses. They're not gonna fire you like them. You don't have, you can actually tell them this is how the whole thing looks like and this is where you can improve and this is how you report but you're not doing well here and this is how you can improve it because you have like say bottleneck down there. So so it's kind of, so in these courses, of course, students learn about actual, math skills and computation skills and modeling and implementation, like programming. At some point, you have to like sit down and implement it. Um, so yeah, I care a lot about students in any course that I teach, even in sometimes even not these big project courses, but even in introductory calculus courses. Um, I don't have them sit down and do like a ton of derivatives. I do at some point, but I always every week have them align right and align what they're doing right now in the class with their own major and how they see their career in the future. And I've noticed that that is not done in academia, and a lot of people graduate having no idea how any of the stuff they learned line up with each other. So I have them write every week, and initially they hate it, and eventually they love it, and they actually learn more about themselves, like who am I and why am I in this school and where am I going with this major. Um, and that is like, again, it's all about aligning yourself and also I teach them writing, even though I'm a math professor, and I actually have them rewrite what they write until it's really pristine and production ready. And I tell them that writing is one of the superpowers in the world. It really is. If you actually know technical stuff and you also know how to write it nicely and clearly and concisely, and you know how to communicate it. And I also have them present every week as well in all my classes every week. So once you like, so I try to like do it, even though it's math courses that I teach, but they learn the math they learn the implementation, they learn the alignment, and they have a purpose of their college. So I tell them about superpowers and all of that, and yeah, so that's how I teach. I hope I answered your question.
One of the key aspects of a teacher, of a guide, is to not only show knowledge, but integrate it into
Yes.
the relevance of the world of the student, where they live and how they apply that knowledge.
Yeah.
I, I think what gets lost in academia sometimes is that people become prescribers or robotic
Yeah.
instruction feeders, but there's no means of okay, what is it that you're doing?
Yeah.
Why are you doing it? How
Yeah.
is it impacting your model? How
Yeah.
is it impacting the world? And how do you communicate it so
Exactly.
people can adopt it? Because if you cannot communicate it to yourself, then maybe you're not clear on what you're doing or why you're doing it. So,
And it's value, like you would not, and sometimes when you're writing this thing you might discover, hey, this is not for me, or there's other useful stuff that this is not, right? And there's a lot of discoveries that happens in that thought process, and in the end, this is their world, right? We are older than them, and we're like the older generation, but this is the world that they're gonna function in, and they're gonna carry it to the next level. So if you're like you said, prescription, if you're going with a prescription strategy, they're not gonna be able to prescribe anything themselves, right? So they have to learn how to carry the world to the next level, and that's how I view my students. I don't view them as, I view them as like this, like brain that's full of potential, and we're gonna like carry them to their potential, not mine, not
right.
my vision, not what I want that do, not, I don't want them all mathematicians at all.
Give them the tools. Give them the tools so that they can write and reason and communicate.
Yeah, exactly. Exactly.
Um, okay, so let's talk a little bit about your PhD program,
Mm.
your course of study, and how that has influenced your work, your thinking, and this view of treating people as holistic
Mhm.
reasoning agents,
Yes,
reasoning or natural intelligence.
100%. Uh, so my PhD program, I was at NYU, New York University. I was at the Courant Institute of Mathematical Sciences at NYU. It's a really strong applied math program. So I did PDEs, partial differential equations. I did material science, mathematical modeling of material science, so materials. Um, and at like the material level, what like all these electronics, in the end they have like little crystals that do stuff that process, I don't know, electricity or whatever. So I was basically doing mathematical models of that and analyzing the models themselves. Um, and to move from a real world application to mathematical equations is an amazing ability. But once you write the math equations that really represent the real world, they are difficult math equations. They have a lot of nonlinearity, sometimes very high dimensions. Sometimes, like every time, like the simplest math is always linear and not many dimensions, low dimensional and linear. But then nature always gives you way more, very highly nonlinear models and very high dimensional, right? There's a lot of atoms in the universe, right? Or there's everything is super high dimensional. Um, so mathematically, you have to simplify your model to be able to do any math with it. Now, the process of simplification is also math, and you learn a lot doing that. And once you have a simplified model, you can do math on it. And the more you want to analyze it, the simpler you have to make it. And then there's a lot of analysis and math that goes in there. So this is to make. I am getting somewhere with this. I was frustrated. I did my PhD. I solved my problem. I discovered, like, say, an energy, and it actually was something good that gave me a PhD. But I was super frustrated because all the math that I did, I didn't feel like it could apply immediately to material, even though I had a PhD in mathematical modeling of material science. I could not apply any of my PhD work into an actual manufacturing of a material, like a new material, anything, right? It did not connect. It was simplified and boiled down to a level, even though I learned a lot of math of it and I solved the math problem, it had nothing to do with the real world. And to me, that was the biggest disappointment in life. As much as I learned and as much as I appreciate my PhD advisor, it has nothing to do with that. It's just how it is. So I actually decided that from now on, anything I work on will have life consequences. I'm not gonna like let this brain not benefit anything in life. Like I will leave the beauty of math to the people who like the beauty of math, but I like to use the beauty of math also in the real world to solve things that have direct impact. So I ended up moving to Michigan and Arbor. I did a postdoc there, and I did work on what's called inverse problem. So you send like a wave down the earth, and part of it comes back, and you take measurements, and from these measurements, you kind of can reconstruct the layers of the earth without actually digging inside the earth. So that was more, applicable. It was still one dimensional, and life is not, earth is definitely not one dimensional. But for you to do any math, so again, I was still frustrated because I still felt, even though I know math, I know how to model, I'm not using my brain for real life. And then I moved to Virginia, and I kind of was some personal circumstances happened in my life, and I had to stop publishing for 7 years. But I kept on thinking, and I kept on working on my projects, but not publishing. I was dealing with a lot of personal stuff, which is very important to get this message out there right now. Is a lot of people tell you in academia, publish or perish. And I actually disagree with that. I think if you have a brain that can think, you will produce when you can produce. It doesn't mean that if you didn't publish for a while, it means that you are a useless person. Now they're going to discard you. No, I mean, you can become successful anytime you want. And I'm a living proof of that. So that's a message out there for anyone who is struggling with anything in their life. Uh, if you have a brain, it's gonna stay and it will produce whenever you can produce. So anyway, in my new university, at some point when I was able to eventually publish, and I was promoted, like now I'm at the final level of becoming a full professor. I'll be a full professor in April. It's now all the way up with the board. Um, so basically I still did not lose time eventually, because when I was able to focus, I did a lot. um, so I decided that I will I it's me this time who's gonna choose a project. I'm not gonna like go to a senior person and tell them, hey, what are you working on, and I'll work with you. It's gonna be me who's gonna choose a project, right? Because I was just wanted to do something that had to do with real life. And so, I was like interested in this machine learning world and all of that. I'm like, oh, I wonder what's that about. And then I open up like machine learning, like a basic book. I'm like, oh, all of this is math. How come no one told me that before? And I'm like, I wanted to give a course on the subject. I'm like, hey, wait a minute. No one is like talking about the math that goes into this, because that would help everybody. So I realized that it hadn't been written yet. So I decided to write the book. So that's just like the story of my PhD, and but one of the most beneficial things that I learned in my PhD is when I specialized in material science. It made me think about things at a very minuscule level, and how it builds up to a macro system. So how the super that the behavior at the smallest scale possible and now at the quantum scale I'm studying helps like affect like on the macro scale, like that transition. So that way of thinking I wouldn't have learned as much as frustration I had with my PhD. It did teach me that way of thinking, and me like now having the confidence to talk about transistors and how they work like mathematically, or like or to tell people about quantum computing. I have the confidence, even though I don't I have the confidence I can pick up the paper and understand what they're doing, and I can explain it at the basic level to the people in my substack. So I have that confidence, and that came from my PhD in material science, even though I didn't use it right away.
That there's a lot to unpack there, and I think it's all valuable. Um, yeah, interesting that you pursued material science, the study of uh, atoms and how they combine to make molecules and how they combine to make complex material, compound material, and yeah, the makeup of the components and the procedures used to construct those components influence their physical and electrical and heating properties. It's such a rich theoretical bed for everything that you're doing now. So I definitely see how you jumped from, okay, let's study atoms and how things work in isolation, and how you chain these things together to build a model of
Mhm.
how an organization works, how a
Yeah.
system works, how data pipelines work. So very interesting.
And I like to see it from the minuscule all the way up, but I also like to see it the other way. I like to see what the up wants and see how to get it to what they want downwards. So I feel like I like to see it both ways, and I like to connect it. And actually, my work now is divided between three main categories of work. I have one category where I am thinking about models, about explainable AI, about all of that, because explainable AI is ultimately like if you talk about policy and regulations, you have to talk about explainable AI. These two are very related to each other. And then the next half of my work is actually solving real life problems with these models. And that's what I do with my projects, with the government, with the military, with whatever. These are actual real life applications. And the third part of my work is the strategy. Is the AI and data strategy at an institutional level, at an organizational level. So we're like building a strategy and aligning and knowing exactly what the institution wants and and then how to align the data and AI strategy with that, or does the institution have to shift a little to take more advantage of these technologies? There's two things there, right? So, and my work is equally divided between the three. Yeah, so foundational, um, real life applications, and organizational. And I actually split my time evenly.
Um, I I think it's interesting that you mentioned you don't just look bottoms up, because bottoms up is more of a theoretical.
Mhm.
Like if these things function in this way,
Yeah,
they should layer to produce this result. But the real world
yeah,
doesn't reflect that. Top down
yeah,
reflects decision makers say we have to go this way, we have to do these
yeah,
things, and then finding how to explain to the top this is
yes,
how the real world physics works. What you
yeah.
want to do may or may not be working, and here's why. So
100%.
it's finding the intermediary between both of those
And
views.
it's so important. You have to find the you have to find that common ground. And I honestly think that what differentiates human as a species and everything else on the planet is that we have the ability to think of goals first and imagine the unexistent first, and then kind of create the tools for that. So I think a lot of people are resentful of top down approach, and you see like you meet people in an organization, the this department doesn't like what what's coming from the top, etc. And because like the little pieces are not seeing the big picture. But I think both ways are important. And a lot of people think that, oh, top down is horrible. I don't see it as horrible. I see it as super important. And ultimately is what differentiates us from everybody else. Like, we can imagine things and make them happen, and create the tools for that, and then make our whole organization. But you have to create also a very good communication structure in your organization, and you have
Yes.
to communicate with people what you want and where they fit in this vision, and what their value contribution is, and how they see it. Maybe they see it because they are down in the, and like the how seeing how things work, they would have a better ideas on how to get there than you would at the top. So I think it's super important to create this communication structure. It's also, I think of it as a graph as well. You can model like the whole institution and its communications as a graph, and you can even layer, and if you want data, you can layer the data. What does data comes and goes out of each of these? So it's super nice, and for me, like that part of my work, I love it a lot. But I usually switch off my brain that's doing the other work, that's explaining things on foundational levels. I switch it off and switch to the like more like strategy organization, and I enjoy both.
I think, yeah, it's an interesting thing to work with people in an matrix environment. I mean, if people don't understand or see the value of the day-to-day actions that they perform,
Yes,
there's a communication problem. There's an
yes,
alignment problem. But
100%.
once that's solved and they get the incentives and they see we're helping people, we're helping animals, we're
Yeah,
making a change, we're building infrastructure, we're
yeah.
bringing heating and electricity to farms so that they can be part of the world. That's cool, but the fragmentation of meaning is what does the psychological punishment. Um,
I couldn't agree more. And people, everybody would be happier at work, and more productive if they saw it that way, or if they whoever communicated that way. And that has to be like somehow part of the strategy, is that communication structure.
let's talk about mathematical modeling
Hmm.
because that is one of the key aspects of this interview and sort of where your area of expertise lies. So, what does that mean, mathematical modeling? How do you take the abstract ideas from bottom up and how do you turn it into a usable working model, map, compass from top down?
Yes. Um, so mathematical modeling, it's funny you ask that, because when I wrote my book, I sent it to my mom and dad in Lebanon. And she opens the book and then she calls me and she's like, my mom is an English teacher, so she taught me English. My dad taught me math. He's a math teacher. And then she says, what does mathematical modeling mean? Because she's an English teacher. So she's like, what does that even mean? All I know is modeling, like actual modeling. Like, what is, and so yeah, so I always remember my mom when someone asked me, what does mathematical modeling mean? So yeah, I had to explain it to her, given that she didn't have any math background. So um, it's okay. Any problem, any not a problem, anything you see around you in real life, you can create an abstract version of it. And you can, and this is the beauty of mathematical modeling, is that anything that is concrete you can literally, whether it's a moving car, whether it's a flying rocket, whether it's the planets, whether it's the galaxies, whether it's how to build a table, or whether it's how to lay materials in your house, literally look around you and come up with something, and you can create a mathematical model, a mathematical description of that system. And which means you can, and you're the one who decides how you're gonna do it. There's not one way to describe something mathematically. So basically you move from a real world project or goal, or say building a house or whatever, into an abstract description of it, and that abstract description is a mathematical model, and that involves how the quantities that you care for in that real world thing interact with each other, how they change with respect to each other. The moment you talk about changing with respect to each other, you're talking about derivatives of the quantities that you care for mathematically, right? So suddenly you can represent what you care for as mathematical quantities that vary relative to other quantities that they interact with, right? So that is you're building a function, or you're building a distribution, or whatever, and then you start writing relationships on how you think they interact with each other. And then once you have this, once you've moved away from the real world to something that you can do math with, you have all this math toolbox that you can evolve yourself, or you can already use things that are from it, and you can look at this behavior, and then you can experiment with this behavior. Well, what if I change the property of the material to you don't have to go to the lab and change the properties to the material. You literally change the numbers in your model that represent that. So it's a powerful tool to experiment and to design and to make things about. The other powerful thing about mathematical modeling is once you learn how to model, you realize that you can model anything in life, but you also discover something very fundamental, is that um, few models describe so many phenomena that are so unrelated, that in your mind are super unrelated to each other. Like, I don't know, how is the evolution, say, of populations related to I don't know, the movements of planets, like things that you would never think are related. But then when you write equations, you're like, oh, it's the same equations that describing this other stuff with the same tools, and you can and you realize that, wow, like this universe can all be described mathematically. And is it written in the language of math? Was it originally written like that? I mean, it's like magic how you actually can describe and design things just by looking at equations, what they do. And this is where the power of computation comes in, because you can abstract all you want, right? You can move from real life to a math model as much as you want, but without the ability to compute these models and see what these numbers are doing with each other, and how to adjust this and how that is, all of this advancement happened, all this explosion in science happened because of the ability to compute. And this is where, and every time we've evolved and expanded our ability to compute, whether you're doing supercomputers or cloud computing, distributed computing, whether you're doing anywhere, we've exploded our ability to compute. We have advanced science because we were able to complexify our models more and describe nature more faithfully, or manipulate what we want to manipulate in our design more faithfully, and actually understand what happens because we have the ability to compute it. Because otherwise, we would be just looking at a bunch of math equations that we have to simplify in order to do analysis. And when we simplify it, it doesn't represent nature anymore. So it really, the computational ability is huge in terms of in doing anything with mathematical modeling. But then the last part of mathematical modeling, so there's a real life to the equations, to the computation of the equations, right? And then back to the real life. If you don't connect it back to solving your actual problem that you started with, or evolving it, or I don't know, building it or whatever, then it's useless in my opinion. Then it's just an exercise in modeling, computation, but that's it. There is no benefit to real world. So it's always good to loop back. For example, like when we got the data from the Fire department, we asked what their goal was. How do you report? What do you do? Blah, blah, blah. We did the math model, we did the computation, but then you have to always like have that feedback loop. Is that, does that align still with your goals? Does it, do we need to adjust? Does it still align? Does it still work? And then eventually they're building the fire station where we told them, depending on the analysis, right? So it all, and it could be in any sense. So I hope I answered you, but it's always moving from real life to math to computation back to real life.
I think with the mathematical modeling, it's a direct tie to the scientific method. I mean, you get this idea of the world by asking questions,
Mhm.
doing statistical analysis, qualitative analysis, quantitative analysis,
Yes,
interviewing the people involved in the system,
yes,
checking to see the decision makers, what are the metrics of success for this project.
yes,
So you get all these parameters and then you say, here's the factors that I deem to be important based on the criteria that you tell me.
yeah,
Here's the way that you chain them in the inputs and the outputs.
yeah,
Here's my recommendations based on what I have.
exactly.
But then you have to try and prototype or ground that in truth because
You have,
whatever idea you have, you don't know.
you don't know, and a lot of people ignore the feedback cycle, and they also ignore it from even
Arrogance.
they even ignore policy and regulation. Like I always ask, like, is this model gonna be compliant if we use this data? I mean, I'm okay if it's not compliant. Then my next question would be, can we push this policy? Can we change it a little? And if that policy is like set in stone, I don't know, Supreme Court, then I'm not gonna model it that way. I'm gonna have to like deviate, right? But a lot of people sit and they start building and putting features and as if like, no, I mean, and I'm not saying that's not a good exercise. It depends what you want. Do you want to learn methods and understand things? That's different than if you wanna like get somewhere with a real entity. And so yeah.
Let's bring that to the concept of material science. You could have really strong you could have a really strong structure, anatomical structure, molecular structure, but if it's a crystal, if it's a brittle sort of material, if it's hit in the wrong way, it will shatter and destroy the entire structure. So
Definitely.
it needs to have some level of tolerance to
Definitely.
absorb, expand, and contract, and
Yeah.
deal with the edge cases, the real world
Yeah.
situations that break that system because it's not so black and white. It's gradient, right? And
100%.
we have to really bridge that gap.
And I consider that as my mission in life, is bridging these gaps. I really do that. Like, if someone tells me what exactly do you do, I'm like, oh, I think I build bridges. That's I what I do.
Tell me about how you're bridging the gap in AI and machine learning in your own practice. I mean, I think you've given me some hints, right? You deal with government and private institutions. They give you projects, ideas that they want to pursue. You build these scientific hypotheses based on mathematical models, and then as they implement, you validate or invalidate, which is
Mhm,
more important, invalidate the
mhm,
wrong assumptions of the project and lead it to success. Because
mhm,
we're here from the standpoint of scientists trying to understand how to build a system and how to integrate it into the real world.
mhm.
But it's a useless exercise if it doesn't translate into real value for real people. Are you saving lives by putting a fire station in the right place? Are you supporting the infrastructure, response time, whatever of the thing that you're creating inside of an existing system? Because
Yeah.
it's just a series of layers of systems,
Yes.
macro and micro. So
100%. I love how you summarize it. Feel like I say something and then you summarize it really, really well. Um, I so the concept of saving lives, that's exactly what's been said to us. Like the fire chief told us, you are literally saving lives. And saying that to my students, you could tell it put them in a different mentality, like, hey, this is real, this is not and in one of the hints I always give to people is that feedback cycle has to be during the time you're building, and you cannot wait until you've gone too far in and you cannot backtrack. You have to like ask the questions, you have to ask their language, and you have to see how their reports say to the government, and see what their metrics they use, and what gets them more funding, and all of that. And sometimes you realize that the problem is not even math or machine learning. You realize that after you ask them all these questions, you realize, oh, it's just a policy change. Like it is. So here's one example of the State Department. One project for the State Department was. About upgrading the cameras in the embassies all over the world from analog to digital. And so when you read like the first two sentences, when you read like the description of the project, you would think it's an AI problem in terms of, oh, you have all these digital cameras, and you want to do the analytics, and it's computer vision, and all of this is super advanced now compared to what you were able to do back in the days of digital. You can do it in real time and all of that. So when we got the project, we thought it's an AI project, right? Computer vision. Um, and then when you like dig deeper and you talk to everybody involved, you talk to the people on the ground, the Marines. The Marines are the ones who protect the embassies, and they are the ones who, and the regional security officers, they're the ones who like are responsible for the feedback from the cameras, whether they're analog or digital, all of that. You talk to everybody involved, people on the ground, and you talk all the way up to these bosses, right? The deputy assistant secretary, and everybody. You talk to everybody in the value chain, and you realize that the problem we were given had nothing to do with AI, had nothing to do with computer vision. They all had that up and running. It ended up being is literally changing the policy in the faculty in the foreign affairs handbook, right? So if you don't, I mean, you could have sat down and wasted your time building an AI system that no one would have used, would have seen no light of the day, right? But what they ended up doing was immediately valuable and was immediately useful, and everybody in the department got a copy of these recommendations, etc. And then another group was working. I think their project was managing the inventory. Like there's a lot of losses in terms of assets not being kept track of, like an actual, automated inventory system. Like this is more like what's that? It's more like supply chain, right? Keep track of all of. Um, how come I forgot that word? The whole field. Anyway,
Logistic?
what? It's not logistics. It's more general than that. So there's supply chain within logistics, and what was operations research, right? It's all operations research, but it's more like the inventory part, like really like predicting when things are getting low and then maintaining them, or tracking where they are. I mean, sometimes things are misplaced, and these are very expensive items or very secure items. So how do you have a system that, given the fact that personnel are always changing, how do you have a system that can track where everything is, and you don't have 500, $700,000 losses every year just because you cannot keep track of your own inventory? It's a big inventory, right? It's a huge assets, and everywhere. They're not located in one place, they're like everywhere. um, in that case, it was a design problem. Like it was like student ended up with a system of like you literally have to like track all of these assets, like with and there's also like with like you have to have databases for all of these assets. You have to have it geolocation for a system, but that geolocation system cannot be wireless because there's security issues. So you have to work with technology. I mean, you could have totally gone the wireless route, and have you not gotten the feedback that no, we cannot use that because we're dealing with secure environments and secure assets. It can be hacked, so none of it could be wireless. I ended up with like GPS, because GPS signal comes one way, not the other way, so no one can hack it. So and they ended up augmenting that with augmented reality. And again, the question was, can they actually use that? Is that too complicated? It turns out they were already so that feedback cycle. So that project ended up being into engineering, all of that. Yeah.
I just want to say, I really like the pure mathematical, like that's just, it colors the way that you view the world, and I just get so much of that. You don't go in and prescribe a solution based on your existing background and expertise.
Yeah.
You look at it as a mathematical equation that
Yeah.
you have to uncover,
Yeah.
because you're not just working on the implementation of a solution,
No.
you're working alongside decision makers to
Yes.
define the problem, identify the constraints, identify the conditions, identify the actors, look at the current decision making processes, looking at the future decision making processes so you can keep making money and keep delivering value,
Yeah.
and then figuring out how to do it all together in a realistic, feasible way. So I
And
really like that.
immediately implementable. None of this stuff, we because of all of this accumulation, and exactly as you described it, this like seeing it at ground up and then up down, and then existing technology, and whether we can deviate from it or not. First of all, it wastes no time to create value, and second of all, almost all of our projects ended up being immediately implementable. Like, I heard so many people lament how their projects go to wasteland. I'm like, oh, that doesn't happen to me, because I don't work that way. I work with the people. It's not like I come here with, oh, AI is gonna save your life. No, most of the time I come, the CEO wants AI, then I'm gonna bring AI. No, let's sit down and see exactly what. Let's like boil it down to your needs and how to get you there, and whether your needs, whether I can also advise you in terms of you can do better, or there's this whole other world there. So it's yeah, it's definitely, I don't it's I never think, I mean, even sometimes my students get disappointed because their project ends up being not right. I mean, it's like there's 5 projects in the class, one of them ends up being not math at all, ends up being policy. Of course it's a disappointment for them, but did they learn a lot about real life and how it works? They did, you know and then they learned math from their other project, from the other projects in the class. They didn't do it themselves because it just didn't work out that way. I'm not gonna like do what I think I want to do. I want to do something that people use.
I think I really enjoy that you teach that to your students earlier rather than later.
Yeah.
Um, Politics and influence have a lot more to do
Yeah.
with decision making than actual real world solutions, how we can actually produce an idealistic society. It's
Yeah.
ego, and it's like
It's
misguidedness or lack of
yeah,
information.
yeah.
It's not a
And then
harmful thing sometimes.
and there will be a lot of politics. There will be a lot of people threatened by what you're proposing, like a whole budget department will be slashed or whatever. And you cannot just sit there and say, oh, they're bad, there is politics, and this is a messed up system. And yeah, it is, you can complain all you want, but somehow you still have to work either with it or around it. If you cannot work with it, you're going to have to work around it. You have to still be diplomatic. There's a lot of interpersonal relations, there's a lot of interviews. Like in one of our classes, students did a combined, in 1 year, a combined probably 265 interviews of individuals in the government in all kinds of positions, like all the way up and all the way at the like technician levels. It's very interesting. It teaches you a lot about communication, people, and at some level, that's what it ends up being. And then your technical knowledge is super handy in that sense. So what I'm teaching in my new Substack is all of that. It has to be all of these skills combined, and then you get places.
Let's I think we can make some time. I'd love to learn and keep learning from you. You have such a pure mathematical mind, and I think it's just wonderful to look at the world from these models, from these ratios, from these simple tools that we can combine to create complex and dynamic systems of reasoning with the world. But let's talk about the pragmatics of it all, because we've sort of guided on the edge and we've made the silhouette of what we want to talk about. But what are the lessons learned where you implement projects to success and you just bring a shared vision to the project?
Mhm. The lessons were learned. That's I think I've been talking about the lessons learned. Uh, who is on the table is very important. If you have a project, you want to see it to success. Who who owns the project? Who are the stakeholders? And is the project how does this particular project align with everything? And are the priorities going to shift with the change of leadership or not? All of that are important to understand about your project before you dive into it. Um, the feedback cycle is super important. The ability to change direction and the openness or even change models. If you notice this is not a good fit, it's totally fine. Expect red tapes. Sometimes you don't have all the data you want, and you're still expected to get an answer to the people who are asking for an answer without all the data you want. You cannot sit there and complain, I don't have the data, so I cannot do anything. You have to either get the data some other way or create a blueprint. If I had the data, how would the model look like? Because sometimes there's security issues around the data that you want, that they literally cannot give it to you, right? And they're still asking you to help them. You cannot say, oh, I really want this. And you can just create a blueprint, or you can simulate some data from a distribution that you think would represent the data that's missing, and use it in your model, and then have them fill it up with real data when they have it, whoever is authorized to get that data. So there's always like workarounds. There's also sometimes, sometimes you can get the data because no one can talk about it, that particular thing that happened, but they still want the answer. So again, always find always have an open mind. And there's also like politics, and also don't try to sound smart. The lessons learned is a lot of people try to sound smart, and listen, we're all smart here, but we want to get this done, and this is very and people start saying like complex words and throwing out, either throwing like, I don't know, some names,
Buzzword.
you know
Yeah.
like like model or whatever, like, oh, this is the hottest thing, and throwing out and complexifying things. Like, don't
Yeah.
I I don't think like that. I think this is, first of all, I don't think it's smart, and it doesn't sound smart. It sounds smart. It sounds like you're kind of trying to use very complex things to answer very
Noisy.
simple. Yeah, making things more difficult. And also some people try to sound smart by taking like cheap shots as, oh yeah, AI is useless, you don't need it, or the cheap shot or on anything they, and okay, you can say that, say it, but be ready to defend it. Be ready to like be asked exactly why you think that and why they think in this case it's not good, because there are some people at a certain level you cannot fool people. Does that make sense? So I feel like the more simple you keep it and the more aligned with the goal and what you're trying to accomplish, that is really the recipe and that is the lesson learned. And so you do learn a lot about people, talking to people, but I think that is a list of lesson learned that I can pull up at the top of. And also you do need technical knowledge. Suppose you have a project that you don't have the technical knowledge for it yourself, because a lot of the time, no one knows everything. It's impossible. Like it doesn't matter how much you know, and sometimes you know it and you've forgotten it because you haven't looked at it in years. um so you're like, oh, okay, this particular problem needs this set of tools that I don't have, say technical tools. Then you have to be open-minded enough either to study it yourself or to like go and ask people to either join your project who know or ask them to teach you because you have this project. So it's okay not to know. No one has all the tools, but it's also you have to like open your mind and either study we all learn all the time, or ask for help from real experts. That usually the faster way is you have no idea how many questions I ask to people. Like I always say, I've never talked to someone who I didn't learn from, including my students. I mean, I learn from people more than they learn from me. So it is so that is also a big lesson learned.
I share that passion of yours. I usually try to, even if you seemingly think you know something, if you ask the same question to many different people, you're gonna get
Yes.
vastly different worldviews,
Yeah.
and they all hold merit.
And
Even
they
if
all
it,
up. Yeah.
even if it's just to feed your own statistical probabilistic idea of the world, right?
100%. And math does teach you that when you see math, when you see the same thing attacked in different from different directions, even from different fields, how they speak about the same problem, and these are vastly different fields, and how they view problems that happen to be in the middle. You're like, wow, that you learn a lot. You learn that that is a nice thing to see. It makes you not kind of narrow, right?
Okay. Well, if there's one piece of advice to somebody who's dipping their toes into AI and they see the tooling and the buzzwords and all that stuff is really cool, is there some advice or dose of reality that you can share with them to approach it with a bit of caution, but in a grounded way?
Yeah. First of all, there's a sea of tools out there, and if you get if you sink in that sea, you'll never get out alive. You will just drown. So don't go for it from a tooling perspective. And there's so many vendors, so much marketing, so much hype. Don't dip your tools that way. More like if say if you are lucky enough to have a real project, let the project guide your learning. What you need for the project, you go and learn it and do it. And so if you're lucky enough to have a real project to work on, if you're not, then I would say, and if you want to go into AI in particular, I would definitely say read my book in Substack for sure. So I'm kind of making people like kind of see it from above that way. Um, um, and, think about the fundamentals. Don't drown in pick the few people to follow. By the way, I learned a lot from LinkedIn. So follow the right people who are talking about the fundamentals of things, and thinking in terms of principles. Once you have your solid principles grounded, then start building on top of that. And always like talk to people, ask them what they're doing and how they're doing it. Like talk to someone who's actually in the field. What are you doing now and how are you doing it? Like I remember years ago when I first started in this field, I would even ask people like, do you program in Python? Like I didn't even know. Like how much do you really use SQL? Like I would ask the most ridiculously basic questions that I didn't know. But just by asking people what do you do and how you do it, you would learn a lot. And then eventually build on that. Yeah. And don't drown in a sea of knowledge. There's a lot this tooling, and oh, I don't know, this is a container, this is blah blah, this is
So many words. There's
and
so
everybody, and you feel like it's like a mob, like they all go here, and then like then yeah, tomorrow they're all going there, and then you're like, hey, wait a minute, just calm down. Like you can't, something technologies cannot like just explode like that and suddenly it's all. And by the way, another advice I want to tell people, which I don't think they realize in their heads, there are two types of organizations. One type is in its DNA, there's data, machine learning, AI, all that is in the DNA. And these are few companies, but they're driving a lot of progress in these technologies. For example, Google, Facebook, Meta, um, 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 a bunch of Apple, IBM, Microsoft, right? So there's these are it's in the DNA, okay? And some of them are better than others, honestly, and some of them have better development culture than others. But we can talk about that later. Anyway, so there's this, but there's also the vast majority of organizations and companies. They are not AI and data native. AI data they're not native, and that is the vast majority. And so do not think that that all the stuff that these people are applying is going to immediately work in your institution, or now because the mob is here I'm going to bring it because this is all. No, your organization is different and is its own thing, and then start with how it works now, and then you might not need a quarter of the tooling of the others. So in my opinion, just separate these two in your head, and then the transition will happen to becoming more data informed, getting more AI value, etc. It will happen, but it will be more organic and slow, and no one is losing their job. So so I feel like a lot of people confuse these two, and everybody, all the mob follows what the DNA, the AI data native ones are doing, without thinking about, hey, wait a minute, my organization is different and my customer base is different in the way I run. So yeah, so I feel like that's a good way to.
I
And I see it actually in my work. I see that very very clearly. Like
I
I'm talking based on experience with on organizational level.
I think that last bit was particularly impactful, and anybody that's listening should take that like at face value. Like that's a really important thing. What are we trying to accomplish, and does AI
Mhm.
hold a major or minor aspect of it? Because
Exactly.
mathematical modeling, things that we've been using since the times of the ancient Greeks,
Oh
and even
yes,
before that, solves a lot of the problems that we have. And then communication solves a lot of the other kinds of problems. So,
exactly. I couldn't agree more. Yeah.
Hala,
We,
it,
go ahead.
it's been lovely to have you. Sorry, you were going to say something?
No, you reminded me of something, but it also left my mind. But it's something along the lines of what you said.
What was it?
It's a good question. I was talking about, you were saying about, yeah, no, it left my mind. It happens to me sometimes. Just um, yeah, I wouldn't remember now.
Well, if you think of it, we'll put it in the post. And thank you again for being a guest.